Welcome to this MOOC on lasers. Today we have come to the last topic as per the course plan, and that is laser safety. So, the laser safety refers to safety of the device and safety of the personnel or the user or the operator. So, lasers are classified based on the output power levels considering harmful effects on human body. So, that is the classification that we are now talking under laser safety. So, first let us look at the safety of the personnel, that is the user. So, what I have given in the following is the classification as per ANSI, that is American National Standards Institution, and the classification includes class 1, class 2, class 3, class 4 lasers and the power levels corresponding to this classification. However, right at the beginning we must note that the actual power levels, I have specified a certain range of power levels, but the actual power levels depend on the laser wavelength, the mode of operation, that is whether it is CW or pulsed mode, and the duration of exposure. However, an order of magnitude power levels are indicated corresponding to these different classes of lasers. So, there are class 1, class 2, class 3 and class 4 lasers. So, let us first take up the class 1 laser. So, the class 1 lasers have powers of the order of 10 microwatt or tens of microwatt, are generally noted as safe lasers or almost harmless lasers. Class 2 lasers, powers of the order of hundreds of microwatt, but definitely below 1 milliwatt, are categorized as class 2 lasers. There are some specific experiments where you need certain lasers of certain specific frequencies, but the powers involved are much smaller and therefore, they are reasonably safe lasers. You can handle them without having to worry about additional precautionary measures. It is safe to handle and work with, but the only advice is do not directly look into the laser beam. So, but do not look into the look is here directly into the laser beam. Let us go to the next class, which is called class 3 lasers. This is further categorized into class 3A and class 3B. I must mention that there are many other classes classification based on various other things, but these are the broad classifications. So, class 3A and class 3B lasers. Class 3A power levels in the range of 1 to 10 milliwatt. Again, they are relatively safe to handle. The normal laboratory lasers which we use in a laboratory, a teaching laboratory, are in the range of 1 to 10 milliwatt. Let us say experiments in optics, interference, diffraction, generally we handle with the helium neon lasers which are of the power range of typically 5 to 10 milliwatt, and these are under class 3A lasers. So, these are safe to handle and work with, but avoid direct exposure of eyes and skin to the laser beam. So, this is very important because as we would know that if there is a, we have discussed when we discuss the laser beam properties. So, if we have a laser beam, a parallel laser beam incident on a lens, then it gets focused to a very fine spot of the dimensions of the wavelength, that is of the order of 1 micrometer here, and therefore, the power density becomes very high or the intensity at the focus spot becomes very high. Our eye has a lens and the lens can focus the laser beam to a fine spot with very high intensity on the retina, and that could damage the retina, and that is why we say never look directly into a laser beam. All right. Now, we come to class 3B lasers. So, class 3B is typically 10 to 100 milliwatt or hundreds of milliwatt. Here it says work with caution, because these are harmful to the human body and of course eyes. Must avoid exposure of eyes and skin to the laser beam, including to strongly scattered light. So, strongly scattered means if the laser beam is incident on a highly reflecting surface such as metallic surface or maybe from some mirrors, then one has to take care that it is almost as strong as the direct beam, and therefore, must avoid scattered beam as well. And it is mandatory that must wear safety eyewear. This is a mandatory requirement, or goggles, and high reflections, for example, as I mentioned, from metallic surfaces must be avoided. So, handling this class of lasers requires caution, and definitely eyewear must be worn, that is safety goggles must be worn. So, this is class 3B. Now, let us go to the next class, which is the class 4 laser. So, class 4 lasers have powers of the order of 1 watt and above. All lasers with power greater than or of the order of 1 watt, sometimes even 500 milliwatt, is classified as class 4 laser. So, the points which are mentioned: work with extreme caution, must avoid, this is the same as for the class 3B, must avoid exposure of eyes and skin to the laser beam, including scattered laser light, must wear eyewear, goggles of suitable OD, optical density. I will discuss about this in the next slide. What is this OD? Suitable OD, and high reflections must be avoided. So, almost similar to class 3B, but this is an additional mandatory requirement that while the laser is in operation, blinking red lights and door interlocking mechanism must be on. This is an additional mandatory requirement when class 4 lasers, namely high power lasers, are in operation. Now, the blinking red light, many of us must have seen outside a laser laboratory, there are always blinking red lights or a board which says laser on, which means you are not expected, not supposed to enter the room. Whatever be the requirement, you can make bell or knock at the door and wait till someone opens the door. Never enter the room where it says laser is on. By requirement that the door should not be locked from inside, and therefore, the door will remain open in the sense it is closed, but not locked from inside. One can open from outside the door, but one should not when the laser red light is blinking or when the board says laser is on. However, the door must have an interlocking mechanism. The door is provided with an interlocking mechanism, that is, in the event of a mistake by a person who enters without knocking or without waiting at the door, when the laser is on, the moment the door is opened, the laser will get switched off. That is called an interlocking mechanism. If a door is inadvertently opened by someone, then the laser would get switched off or the beam would be cut off by the requirement, because the person who is entering is not wearing the safety eyewear. So, that is called the door interlocking mechanism. So, these precautions must be followed. This is the essential ones. There are several others, but the essential ones which are listed here must be followed when lasers are operated. All right. So, Let me explain what is this optical density OD, because if you take a laser goggle or a eye safety wear, it is always written there OD equal to 5 or OD equal to 6. What does this OD mean? So, OD stands for optical density and it is defined as minus 10 log power transmitted divided by power incident, or intensity, transmitted intensity by incident intensity. So, which is nothing but it is minus log. So, you can interchange it and make it as log to the base 10 P incident, power incident by power transmitted. Thus, for example, if OD is 5, that means if OD is 5, that means this term here is 10 to the power of 5, because log of 10 to the power of 5 is 5, which means the transmitted power is 1 by 10 to the power 5 times the incident power, or 1 by 100,000 times, 100,000 is 10 to the power of 5. So, the transmitted power is cut down by 100,000 part. So, for example, the table which I have shown here illustrates this. If OD is 0, which means there is no blockage, that is P transmitted is equal to P incident, which means it is 100% transmission, 0% attenuation. If OD is 1, that means the transmitted power is 10% and 90% of the incident beam is attenuated. 1% means, that is OD is 2, means 1% is the transmission, and so on. And when OD is equal to 5, the transmitted power is 0.001%. So, if there is a 100 watt laser, so let us say there is a 100 watt laser operating, and by chance the laser beam is incident on the goggles, which says the OD is 5, then the transmitted power will be 10 to the power of minus 5 times 100. So, 100 into 10 to the power of minus 5 watt, that is 10 to the power of minus 3 watt, or 1 milliwatt. So, there are, in particular when you operate with very high powers, hundreds of watt, OD of 6 or 7 is used. I have not shown here 6. Normally, when one operates with the Nd:YAG lasers, which is of the order of hundreds of watts, OD 6 or OD 7 is used. Even though you are not seeing the beam directly, but the scattered light itself could be harmful, and therefore, typically OD 6 or OD 7 is used. Now, one other point is, this is okay if you are using Nd:YAG laser. So, all these safety goggles have a stop band and a pass band. So, if you plot it as a function of lambda, then if you are talking of the attenuation alpha, then if you are operating an Nd:YAG laser, generally it will have a stop band. This is what I have shown is the loss coefficient, not transmission. So, generally around 800 nanometer here. So, nearly equal to 800 nanometer to 1600 or so, generally nanometer. So, this is the loss. In terms of the transmission, then I could show. So, this is lambda versus transmission. If I plot that, generally, so let us say this is transmission is 100%, then when you use the goggle, then the transmission is slightly lower and then it drops down like this and almost blocks. So, transmission, what I mean is, if you have put the goggle here, so I am showing the glass only and the laser beam is entering or the scattered light is entering, then transmission is the fraction which is coming here. So, this is the transmitted fraction and this is the incident, and this is with a certain OD. Then the wavelength spectrum almost it blocks the window. Let us say if you are using, as I mentioned, this is Nd:YAG. So, Nd:YAG is at 1064 nanometer, and therefore, in the visible region the transmission is reasonably good, and therefore, you would be able to see all the laboratory components, equipments, everything in such a case. But suppose you are using a high power laser which corresponds to the visible region. Let me show here with a different color. So, suppose you have a laser, a high power laser which is giving output here, let us say like the argon ion laser at 514.5 nanometer, then you have to have a notch filter, or the filter transmission has to drop rapidly like this around this, so that it can block the laser light. Because if we block the entire region around this line, then the goggle will not permit the visible light to pass through, and the laboratory would look like a dark room, and you would not be able to see the equipments. So, appropriate goggles have to be chosen. So, there are several issues involved in choosing the goggle, but the most important is optical density, which has to cut down the laser beam, so that it does not harm the eyes. All right. Next we come to safety of the laser. This is a very broad topic, because there are various precautionary measures to be followed depending on the type of the laser as specified by the manufacturers. So, what kind of precautionary measures? For example, electrical power requirements, the operating voltage, operating current, temperature, etc. Protection against thermal and mechanical shocks. For example, if you are operating a helium neon laser which contains a quartz tube inside, then one has to handle the laser head very carefully, otherwise it could lead to damage to the tube and to the laser. And therefore, mechanical shocks, mechanical vibrations, not all lasers can withstand. So, that is what is meant by mechanical shocks. Thermal shocks, sudden variation in temperatures can also damage the laser material, and then protection against static charges, ESD, electrostatic discharge. This is very important, particularly for semiconductor lasers. So, semiconductor lasers, in the case of semiconductor lasers, is very crucial to take care of protection against static discharges, semiconductor lasers. So, there are various types of safety measures to be taken to take care of the laser or for the safety of the laser. There are, I have not listed many of them, because it depends on the type of the laser as specified by the manufacturers. All right, that brings us to the end of this laser safety. There are many more issues which may be discussed here, but we will stop here on this topic. But before I stop the last lecture of this course, I want to very quickly recap what we have covered in this course. So, let me make a quick recap. So, this is the introduction to laser MOOC, and as per course plan, we started with a general introduction here. So, these numbers here are the lecture numbers. General introduction, where we discussed about what is a laser, what are the three components of the laser, and then the scope and contents we discussed in this first lecture. The components, as we know, includes an active medium. When pumped appropriately, gives rise to amplification, and an amplification with a suitable feedback mechanism leads to an oscillator or the laser, which is the source of electromagnetic radiation. It is a coherent source of electromagnetic radiation, and therefore, we picked up in part 1 the interaction of radiation with matter, and in this we started with the Einstein coefficients, then we introduced atomic line shape functions and discussed the condition for amplification by stimulated emission, and then we introduced line broadening mechanisms which determine the line width of emission of the laser. So, we discussed both homogeneous and inhomogeneous broadening mechanisms. And then we continued on to part 2, where we discussed various schemes of amplification, and therefore, to discuss this we considered first a 2-level system and then 3-level system and 4-level system, and under what conditions we can achieve amplification by stimulated emission. The condition for amplification we had shown earlier that population inversion is the necessary condition for amplification. Now, how to achieve population inversion? This is what we discussed in this part on scheme of amplification. What is a suitable scheme to achieve population inversion and hence amplification? Then I picked up laser amplifiers as an example and discussed the Nd:YAG laser amplifier and erbium doped fiber amplifier. This is a very important device in optical fiber communication, widely used, and therefore, I specifically took this and we discussed erbium doped fiber amplifiers. Then we came to part 3, because optical resonators is an essential part of lasers, and it is the optical resonator which determines most of the important properties of the laser. And therefore, we discussed the resonance frequencies, the spectral response of the optical resonator, and how the resonator loss and cavity lifetime determine the spectral response. Then we picked up spherical mirror resonators, which are the widely used resonators, and using the ray theory we obtained the resonator stability condition. We then used a matrix approach to trace rays through the resonator, ray paths in a resonator, and then subsequently we went on to discuss transverse modes of the spherical mirror resonator. So, these are the Hermite-Gauss modes of the spherical mirror resonator, and the fundamental member of this family is the Gaussian mode, which we discussed in a little bit more detail. So, lasers have longitudinal modes and transverse modes. Longitudinal modes refer to the resonance frequencies, and transverse modes refer to the field distributions, transverse field distributions supported by the resonator. And in this section we also discussed how to select a single transverse mode and how to select a single longitudinal mode, because this is very important to realize single frequency lasers which oscillate in a single longitudinal mode and a single transverse mode. Then we came to part 4, where we combined the amplifier and the resonator to make the oscillator or the laser, and we discussed laser oscillations and the threshold condition for lasing. An important aspect of spectral hole burning in inhomogeneously broadened laser medium is also discussed. And then we discussed the variation of laser power around threshold, that is, as soon as you cross the threshold, if we quickly recall, the photon number shoots from a small number to a very large number by orders of magnitude around the threshold pumping rate R is equal to R t. And then we also discussed the optimum output coupling, which is a very important design issue in a laser, that at an operating power one can design the output coupler to have optimum reflectivity, which would give the highest output power. So, then we discussed the characteristics of the laser output, the properties of the laser beam, and also what determines the ultimate line width of a laser. And we have seen that it is the fundamental limit is imposed by spontaneous emission, determines the fundamental limit of the laser line width, spontaneous emission. Then we took up pulsed lasers and the methods of pulsing, various schemes of pulsing, Q switching and mode locking being two important methods, and specifically I picked up the methods of mode locking in this part. We then came to the last part where we picked up some laser systems and applications. As mentioned therein, there are large number of laser systems and each one has its own specific advantages, disadvantages, construction, output wavelength, power levels and so on. Similarly, laser applications are enormous number of applications of lasers, and these there can be full courses on laser systems and laser applications. So, our objective was to just indicate some of the common laser systems, so that we understand that yes, these systems indeed are consistent with the theoretical description that we had undertaken. All right. In particular, I picked up fiber lasers and semiconductor lasers in a little bit more detail, because these have very large number of applications, both semiconductor lasers and currently the fiber lasers for various industrial and commercial applications. As an illustrative example of laser application, I picked up optical fiber communication as one of the examples, lasers and laser amplifiers, the erbium doped fiber amplifiers and the semiconductor lasers which are used in optical fiber communication, and a scientific application of lasers in nonlinear optics, and finally laser safety. That is what we discussed today. That brings us to the end of this course, an introductory course on laser. I would like to emphasize that it is an introductory course. Laser physics is much more involved. Laser is a quantum electronic device. Therefore, to go into the depth of lasers, it is necessary for us to understand quantum electronics. A course on quantum electronics and quantum electrodynamics will prepare you to go into the depth of laser physics. But the objective here was to introduce the essential aspects of lasers. All right. With that, we come to the end of this course. I have greatly enjoyed in presenting this course at this introductory level, and hope it motivates some of you, some of those who have attended this course to take up further into the depths. So, before I stop this course, I have a slide which shows if you are interested, how would you pursue this area. So, that is what I will put as the last slide. So, here, so this is of course, most of you would have gone beyond 12th, and if you are doing BSc, then you could go over to MSc with physics or electronics, and then you could pursue any MTech in the areas of applied optics or optoelectronics, optical communication, laser technology, photonics. There are several MTech programs of these titles in the country, and then you could, if it interests you further, you could go for a PhD program, or you could go from here itself seeking some jobs after MTech, or you could pursue a PhD. Similarly, if you are an engineer, if you are doing a BTech in electrical electronics, ECE or engineering physics, it is possible to get admission in these MTech courses or a PhD directly in this area of optics and lasers. And then beyond PhD, one could go to several industrial R&Ds or academic and R&D organizations. So, this is the way which I have charted that one could pursue a future in this area if the area interests you. Thank you. I will stop at this point.